3D printing techniques over a wide range of applications, a wide range of different materials that can be processed for the different items which need to be produced. It's very efficient in terms of usage of the materials, because for long-term missions you can't have supplies, so you need to maximize the use of what you have with you on site. And also it can be automated. You don't have to use the available time for the crew. So for those reasons, we think 3D printed is very well suited for future long-term exploration missions. So the vision for 3D printing for optimal use in space exploration is that we will use these techniques in order to make the maximum use of the materials that we have on site, so that we become somewhat independent of the Earth and of constant supplies from the Earth. We could use 3D printing for reusing and recycling the materials that we bring with us. Let it be plastics, metals, human waste, for example. And we could also use 3D printing to use the materials we have around us. The regolith, for example, could be used for construction purposes, to make hardware, to make solar cells from the silicon which is included in the regolith. So the idea is really to have a settlement which is not only independent but also expandable. We are not limited by the modules that we land on the surface, but we can expand by using the materials that we have around us.
Additive layer manufacturing has this great potential, not only because it's a break rule on Earth in the manufacturing process, but because it will enable and make this adventure to space each day closer and closer. Additive layer manufacturing, to be useful and really an help for space production, has to be integrated in a process chain. It means that it has to be as much as possible self-sustained, because if we are able to feed the process by itself, we can really take the maximum advantage of this technology.
So the printer that has been produced by the consortium is very robust and is capable to print engineering thermoplastic like PEEK. That means polyether ether ketone. So this plastic is very interesting because it's one of the most resilient thermoplastic, very high thermal resistance, but also biocompatibility. The printer needed to be tested, and of course all the tests were performed to meet the operational requirement of the International Space Station. But moreover, we needed also to see if this printer is capable to print functional parts that can be useful for the astronauts in ISS. So when we speak about 3D printing, we also think about, you have to think with 3D printing mind. So when you think about 3D printing, the goal is not to take a design which is already existing and replicate it. Indeed, the printer is capable to do this. So this is a container made of PEEK. But in order to take advantage of this manufacturing technique, you need to optimize the design. And the consortium was capable to create and to make new design that is more suitable for the 3D printing process. So same examples, as a functional part, we wanted to see if we can print connectors for gas or liquids. And this is an original design of a connector, and this is the optimized design of the connector. So this design allows the connector to sustain 10 bar of pressure. Same, we have the end fitting of the connector. You can see original design, where you have a flat surface, and optimized design, where you have some kind of slope that increase the mechanical properties. It's clear that with the achievement of this project, MELT project, we can see that functional parts can be produced within an environment which is suitable for the International Space Station, and this functional part can be used to replace failed parts. We are very satisfied with the outcome of the MELT project. The breadboard produced is very robust and meets all the requirements that were set initially. The difficulty of this project was to use out-of-the-shell technology and to change this technology to meet all, let's say, space requirements and moreover all the operational requirements of the International Space Station. For this purpose, we decided to go directly to the most difficult, let's say, polymer, and we choose to process PEEK. The difficulty with peak processing is to control all the thermal environments during the printing process. The consortium did a great job, and we can see that the quality of the final part is very acceptable, there is no defect, and moreover the functionality is ensured.
To design the printer, we have to take in consideration all aspects of living in ISS. So safety aspects were very important. The time of the astronaut was even more important. We spent a lot of money taking stuff into space, so we have to make sure that everything that we put on the printer was high-grade materials and with the best performance that we can get.
So in this project, another interesting point is that we have achieved to mix two different specialties, a manufacturing specialty, which is 3D printing, and to use specific raw material like engineering thermoplastic. So with this thermoplastic, we were able to build functional parts, and we can see that these functional parts can be adapted to existing parts. This is very important because the combination of this technique and the material will allow us to think new maintenance strategy, where we will basically get rid of spare parts to print parts in situ on demand.